Okay, I'd like to solve one last problem, or at least set up one last problem. We don't need to go through all the steps. But just imagine, right, in the movies all the time, we've got somebody who falls over the edge of a building or of a cliff and is holding onto a rope, and then somebody on the land who is trying to pull them back up. Or maybe they're lowering them down. So let's just ask. Let me just, in order to set up a problem to see some interesting things. Let's just make the surface frictionless, so just we don't have to worry about it. And so clearly, the person M1 is not going to be able to stop M2 because there's no friction to hold on to. Okay, but they're going to be able to slow down M2. Okay, so the first question is what is the, well, the first question, the question is what is the acceleration of M2 as M2 falls? And the acceleration of M2 as M2 falls is not the acceleration due to gravity. A common mistake here is to just assume that it's the acceleration due to gravity and then solve things in the problem using that. But why is M2 not accelerating at the acceleration due to gravity? Right? If I want to know what is the acceleration of M2 in the downward direction, why is it not the acceleration due to gravity? It's because M2 is not in free fall. Free fall means that is under the influence of only gravity and no other force. M2 has another force on it. Which one? It's got a rope attached to it. It's got a tension on it, so it's not falling at the acceleration due to gravity. So the question is how do we set up this, how do we solve the problem for what is the acceleration of M2? And I'm just going to talk about the setup. Okay, we've already drawn our diagram. Now we're going to draw free body diagrams. So we've already done step 1, draw our diagram. Step 2, we're going to draw our free body diagrams. And I'm just going to draw a free body diagram of M1. And the free body diagram of M1, go through all your steps. You'll find it is Ft up, Ft to the right, Fn1 up, and M1g down. Fg down, M1g down. Okay, and no friction, right? M2, free body diagram, it's got Ft up and M2g down. So the force due to gravity, which is the weight, which is M2g down. You can write it as Fg1 and Fg2 like I have, but in this case I'm taking a shortcut and just writing M2g. Right? In general, remember that Fg is always equal to mg for any body. Okay. That was actually a parenthetical. Okay, a couple things to notice here. Yes, I plugged in Fg, but the important thing to notice here is that the tension force on M2 is the same as the tension force on M1. Actually, it isn't the same. Got to be careful. It is the same only if, so we can make this Ft1 and Ft2, it's the same only if the pulley, the thing, in this case I actually drew a pulley. I never said that, but I drew a pulley. That's this thing here, right? The pulley. I drew a pulley in order to reduce the friction on the rope. And what we can actually say or even show is that if, whoops, hold on. Okay, so the important thing here is that the pulley, which we're just modeling this system to be the rope going over a pulley, if the pulley is frictionless and massless, if it basically has no real impact on the rope, it won't exert a force on the rope in the direction of the tension, and therefore it doesn't change the tension. Not like the problem where we had the person with ropes pulling in either direction on the person. They changed the tension because they had a mass. In this case, therefore, if the pulley doesn't really impact the rope, if it doesn't have tension, for a mass or friction, then the two tensions, Ft1 and Ft2, are the same, and we'll just call it Ft. So we've got the same tension on each box. So that's just allows us to know that Ft1 is equal to Ft2. Okay, so then we go ahead and we want to do step 3, which is to choose our positive directions. And remember, now here's another key difference with this problem and other problems we've seen. Our plus x direction, let's do for body 1, plus x direction, whoops, let me do it in a different color. My plus x direction is the direction of acceleration. Body 1 will accelerate to the right. So I make plus x to the right and plus y perpendicular to that. Now the plus x direction for body 2, now I'm going to choose a different axis than for body 1 because we're treating these separately. They're free body diagrams. They're separate bodies. And again, it should be that the plus x direction is the direction of acceleration. So I'm going to choose for body 2 plus x to be down, because I'm applying Newton's second law separately for body 1 and body 2. And as long as we choose the plus x direction to be consistent, in other words, body 1 will accelerate to the right at the same time that body 2 will accelerate downward, right? So they're consistent. They're consistent. So a positive acceleration for body 1 will also be the same positive acceleration a sub x for body 2. So we actually want to switch our axes like this for body 1 and body 2. Okay, so we've chosen our direction. Step 4 is write down the relationships we're going to use. Step 5, I'm going to apply, look at what f net x and f net y are for body 1 and body 2. Now, let's go ahead and do that. For body 1, right, for m1, we've got ft1 equals m1 a sub x. That's the x direction. And in the y direction, we've got fn1 minus m1g equals m1 a sub y. And for m2, we've simply got m2g, because that's in the plus x direction, minus ft2, which is in the minus x direction, so that's the minus sign, equals m2 a sub x. So we've applied and so if you didn't get that, take your time, look at it. We're just identifying the net force from the free body diagrams on M1 and M2. And then step 6 is to recognize the we know what M1 a sub x is the same for both, so a sub x's are the same. We didn't use subscript. A sub y is equal to 0. M1. Right. I didn't actually give you M1 and M2. What the question I asked is what is the acceleration, and really what I meant is what is the acceleration in terms of M1 and M2. So step 6 is really just to recognize that a sub y is equal to 0, and so now step 7, solve for a sub x. Solve for the acceleration. So now we're just going to solve for a sub x, which I'm just going to call a because it's the only acceleration left. And remember that ft2 equals ft1. We're just going to call that ft. Note that the second equation of these three simply tells us about that the normal force is equal to the weight. It doesn't tell us anything about the motion. And so we're really just taking the first and the third equation, and solving those together. Do the algebra, and you'll find that solve those together, cancel out ft, do the algebra, you'll find that acceleration equals m2 over m1 plus m2g. Oh man, I'm so sorry, I forgot jokes. Okay, so a ham sandwich walks into a bar and orders a beer. Bartender says, sorry, we don't serve food here. Why did the Clydesdale give the pony a glass of water? Because he was a little horse.